A curve is a set of points in R3. It's a geometric object. Now, last time we talked about a path or a vector function. This is a rule that tells us how we should move along the curve in R3. Another way to interpret it is that this vector function R is a rule that tells you how to bend that straight line interval A to B into the curve in R3. But what we're going to do here is attach a physical meaning in addition to the geometric meaning. So to begin with, in a physical interpretation, t will represent time. This vector r of t will represent position at time t. We're going to introduce several vector quantities. Now, you may recall from physics that displacement is a vector. If you've got a curve and you've got r of t, here is another point, r of t plus delta t. By using the tip-to-tail rule for addition, there is a vector that connects these 2 points. And this vector I'm going to call the vector delta r. And this is the displacement vector. The displacement vector tells you how to get from r of t to r of t plus delta t. It tells you how far to go, and it tells you what direction to go in. From vector addition, this displacement vector is simply the difference. The displacement is given by this delta r. The size of the displacement, that would just be the distance, how long that displacement vector is, the length of this difference. The next natural quantity to talk about is velocity. We're going to be talking about the instantaneous velocity, which is the velocity at one moment in time. You're going to calculate an average velocity, where you're going to take the displacement, divide it by delta t, and then let that time interval delta t shrink to 0. So in other words, calculated by this difference quantity. Now, we've already seen this difference quantity when we talked about the derivative of a vector function. So this is the derivative if this limit exists. R prime of t is the velocity as you move along the curve. If r is not differentiable, you won't be able to calculate this velocity vector. There's a geometric connection as well. If we have a curve, the position is given by this r of t. Here would be the vector r prime of t, which in this definition would be v of t. So the velocity is always tangent to the curve at the point r of t. The velocity is a vector that can be slid and attached to the curve right at the point r of t. Now, the speed is simply just going to be the size of this velocity vector or the size of the derivative. It's the scalar quantity that tells you how fast, but not which way. Now, the final quantity that we're going to talk about is acceleration, the rate of change of the velocity with respect to time. This is essentially calculating a derivative of a derivative. This will be the second derivative of the position function, of the vector function. This vector function has to be twice differentiable in order for the acceleration to exist. So why do we care about the acceleration? The answer here is Newton's second law. So Newton's second law tells you that the net force acting on an object, and this is a vector sum, is equal to the mass times the acceleration of that object. So what this ends up giving you is an equation. From the acceleration, you can find the velocity, and from the velocity, you can find the position. So this is what's called a differential equation. It allows you to figure out where your object will be based on the acceleration that's acting on it. Now we're going to look at a very important example to do with circular motion. And essentially, it's just like this title says, you are moving along a circle that's centered at the origin that has a radius of r. Now, the set of points is described in Cartesian coordinates, x squared plus y squared equals capital R squared. Now I'm going to give you two parameterizations that will describe how to move along this curve. So we will have one parameterization, r cos t, r sine t, and the other parameterization will be r cosine of 2t, r sine of 2t. Now note, in the first case, r cosine of t squared plus r sine of t squared, this is going to produce an r squared with a cos squared t plus sine squared t, which does in fact give me a 1. So this gives me an r squared. So r1 does satisfy the equation of this circle. For the other parameterization, r cosine of 2t squared, r sine of 2t squared. As before, there's going to be an r squared, cos squared 2t, sine squared 2t. As always, as long as the period of these functions is the same, that's going to give you a 1. The second parameterization does in fact work for this unit circle. So let's compute the velocity, the speed, and the acceleration for both of them. So v1 is going to be the derivative of the first parameterization with respect to t. It's the derivative of r cos t, so it's going to be negative r sine t. The derivative here would be r cosine of t. The speed, which is the magnitude, is negative r sine of t squared plus r cosine of t squared. This is going to end up giving me a root r squared, which is r because this is assumed to be a positive. And the acceleration is the derivative of the velocity. So if I were to differentiate the velocity function that I got, I'd have negative r cosine of t, and then I would have a negative r sine of t. r1 of t was this function, r cos t, r sine t. So that's just a computation related to the first path function that I've given you. Now I'm going to do the same thing for the second one. R cosine of 2t, r sine of 2t. The velocity, which would be the derivative of this function, I have to use the chain rule, and I'll now get 2r sine of 2t, and I'll get a 2r cos 2t. The speed, the length of this vector, I'd have negative 2r sine 2t squared, 2r cos 2t squared, taking the square root of all of this, 4r squared, which is going to end up giving me a 2r at the end of the day. And then the second acceleration function is simply the derivative of the second velocity. I have to use the chain rule again, and this is going to end up giving me a negative 4r cos 2t and a negative 4r sine 2t. Now again, all of this is simple computation, but I want you to notice that there's some interesting things that happen. In the first case, the speed of this curve was r, whereas in the second case, the speed of the curve was 2r. So moving along the points in the circle according to path 2 causes you to move faster. So r2 causes motion that is twice as fast as r1, because the speed for the second path was 2r, whereas the speed in the first path was r. Now, if I were to take the path of the first case dotted with its velocity, r cosine of t, r sine of t, dotted with negative r sine and an r cos. And what I would end up getting would be a negative r squared sine t cos t plus r squared sine t cos t. That gives me a 0. If I were to go r2 dotted with v2, dotted with negative 2r sine 2t, 2r cos 2t. What that ends up giving me is a negative 2r squared cos 2t sine 2t plus 2r squared cos 2t sine 2t. Guess what? That's a 0 again. Is this a coincidence? No. So for circular motion, we always have r dotted with v equals 0. That means that any point, the velocity will be perpendicular to your motion. If you are moving along a circle, the distance is always the radius of the circle. That means if I squared the length, it would be some constant squared, which is some constant. The length of a vector squared is r dotted with r, and that equals a constant. So if I were to take the derivative of both sides, well, I know that the derivative of a constant is always 0, and I know from the product rule that this is going to give me an r dotted with an r prime plus an r prime dotted with an r, and that's 0. 2r dotted with r prime is 0, which implies r dotted with r prime is 0. It's always the case that position is orthogonal to velocity. Similarly, the acceleration is a multiple of the position vector, but it points in the opposite direction. So for example, in the first parameterization, we had r cos t, r sine t, and when we talked about the acceleration, we had a negative r cos t and a negative r sine t. So it essentially means that when you are moving along a circle, your acceleration vector will always point in. And this is what's called centripetal acceleration. And centripetal is a fancy word for center seeking. That means it points into the center of the circle. Another example has to do with Newton's second law. Suppose some object that has a mass equal to 1 falls in a constant gravitational field with acceleration g is equal to negative 10 in the k direction. What we would like to do is find the velocity and the position if v at time 0 is I plus j minus k, and then the initial position, r of 0, is 2I plus a 3j. So Newton's second law says that the vector sum of all the forces acting on this object are equal to the acceleration times the mass. The only force that's acting on this object is the force of gravity due to the gravitational acceleration. So the m's will cancel out. And we've already been told that the acceleration vector due to gravity is given by 0, 0, and negative 10. And this is equal to a of t. So from this, we are going to be able to find the velocity. The definition of acceleration is that it's the derivative of velocity. So if I'm looking for a velocity, I need to undo this derivative operation using the inverse operation, which is anti-differentiation, and this tells me how to calculate the velocity. So the velocity is the antiderivative of the vector 0, 0, negative 10 with respect to t, with respect to time, essentially equal to the antiderivative of each component, which is going to give me some c1, c2, and then c3 minus a 10t. Now, the initial velocity was ij minus k. If I were to plug in time is equal to 0 in each of these, this would tell me what those constants are. So the velocity here is the velocity function. Since the velocity is defined as the time derivative of position, that means if you want to find the position vector, all you need to do is take the antiderivative of the velocity. And so if we are to anti-differentiate the velocity function, we're taking the antiderivative of this particular expression, according to the last lecture, the antiderivative of each component. And if you go through and follow through, you'll get a t plus c1, t plus c2, and then in this component, you'll get a negative t minus a 10t squared over 2 plus a c3. The initial position will allow us to determine those constants. That's c1, c2, and c3. So it's possible for you to solve Newton's second law to determine the velocity and the position